Welcome back to chapter 19. We're going to continue. As you can see, we're picking up with section 4, which is on capacitance. We're picking up with section 4 on capacitance. So a capacitor is a device that's used in an electric item to store electric charge. Sometimes they call it a condenser. It used to be that one of the most common places you would find a capacitor would be in disposable cameras that have little flash units on them. Now that everybody's cell phone takes a picture, I don't think disposable cameras are all that common anymore. So you may very well never have actually used one. In an electronic device, capacitors can look like all kinds of different things. They can be really small, like the size of somebody's thumbnail, or even the nail on your little finger, or even very big, like the size of a gallon of milk, or even larger than that. So these are all kinds of different capacitors in this photograph. You can see the little flat ones that look like a wafer, and these are tunable capacitors. They have little metal fins that can be moved into and out of that'll change the value of the capacitor. And then you have these standard cylinder size ones. These are all relatively small. But anyhow, an assortment of capacitors in our photograph. So capacitors are used for a variety of things in electric circuits. They can be used to tune the frequency of a radio receiver. That's one of those where you'd use a variable capacitor to eliminate sparking in some kinds of ignition systems, to store energy for short times. This is how it was used in electronic flashes, and then there are an assortment of other uses for it. So basically, all capacitors have two conducting objects that are close to each other, but they don't touch. If it's a parallel plate capacitor, you connect it to a battery, and you would have the formula Q equals C multiplied by V. Q is the charge on either plate in coulombs. C is the capacitance measured in farads. And V is the electric potential, or the voltage measured in volts. So Q equals C times V, or sometimes I'll write it as Q equals V times C because of that home shopping club that's on cable TV sometimes. But we'll need to know Q equals CV. So Q equals CV is an important equation for us. As I said, capacitance is measured in farads. It's measured in farads. The abbreviation is capital F. A farad is a really big number, and so typically you'd find capacitance in picofarads or nanofarads or microfarads or millifarads. So we almost always use fractions of a farad. In a circuit diagram, or a schematic diagram, a capacitor is indicated in one of these three ways. You might have a drawing where there are two parallel lines. That's a capacitor. You might have one where there's a straight line and then a curved line. The straight line is the positive pole on the capacitor. The curved is the negative. Or you might have one where it's those parallel lines and then there's an arrow drawn through it, and that's a variable capacitor. That's one of those you could tune by moving the plates in and out. These are just three different ways capacitors would show up in a circuit diagram. We want to talk about a simple parallel plate capacitor. So simple parallel plate capacitors have two plates, and this is a really big one used for demonstration purposes. So a big plate on the right, a big plate on the left. And you can see they're on stands that move back and forth. So there are things that can be inserted between the plates. You could have just a gap of air. You could insert some paper or a piece of glass or a piece of plastic. Whatever you put in between is an insulating material, and it's called a dielectric. And we'll talk about that in a minute. So you don't need to know the general formula. I'll tell you when we get to the specific one. it is important to know that epsilon naught, that's what this funny little thing that looks like a script E with a sub-zero on it. The little script E is not an E, it's a lowercase Greek letter epsilon. And this sub-zero that we have, because originally zeros were referred to as naught, N-A-U-G-H-T. So this, instead of saying epsilon sub-zero, it's epsilon sub naught, and that's something called the permittivity of free space. And in this instance, free space is basically a vacuum. You don't need to memorize the value of 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared. It'll be given for you. So just like you didn't need to memorize little k, you don't need to remember epsilon naught. You look it up. All right, and little k and epsilon naught are related to each other by this equation, which again, you don't need to memorize. So let's look at dielectrics. Dielectrics are the materials that you put between the plates on your capacitor, the materials that go between the plates and the capacitor. So it keeps the plates separate but close together. It is always, the dielectric is always some sort of an insulator. It could be air, it could be a vacuum, it could be a plate of glass. There are lots of different things. Dielectrics are used to allow your plates to be close without touching. That's because the smaller you can make the separation distance, the larger your capacitance. It will also prevent the charge that builds up on the plates from discharging spontaneously. That's referred to as breakdown. So that allows your plates to hold a higher charge. And it will allow you to increase the capacitance, remember that's capital C, by a factor of kappa. Now this is not a capital K, this is a capital kappa, a Greek letter, which is the dielectric constant. So we've got our two conducting plates, and then this darker blue is our dielectric. The darker blue is our dielectric. For any parallel plate capacitor, we need to know the equation that capital C is equal to kappa epsilon naught A over D. Kappa epsilon naught A over D. You need to know this equation, C equals kappa epsilon naught A over D. You don't need to memorize the value for kappa. You can look it up in a chart. Kappa is the dielectric constant. And again, epsilon naught will be provided, and you'll either know A and D and have to find C, or C and D and have to find A, or A and C and have to calculate D. So depending on the material, the dielectric constant will vary. You can see for a vacuum, it's 1. For water, it's 80. And there are other numbers in between. So let's look at an example. So we want to know the capacitance, remember that's capital letter C, for a capacitor with a paper dielectric. So we'd want to look up paper in the chart. Its dielectric constant is 3.7. And we know that the plates have an area of 0.2 squared meters, and that they're 0.5 millimeters apart. So we write down what we know, what we're trying to find in our formulas. So kappa is 3.7, we looked it up in the table. The area is 0.2 meters squared. Epsilon naught, they would give us, so 8.85 times 10 to the minus 12 coulomb squared per Newton meter squared, and little d is the separation distance. They told us it was 0.5 millimeters, so that's 0.5 times 10 to the minus 3 meters. We're trying to find capital C, the capacitance, and we know that C is equal to kappa epsilon naught A over D. This is our formula. So we start out by writing the formula, and then we plug in. We write down our formula, plug into our formula, and do the math. Well, notice I use a lot of parentheses, and the first time I plug in the numbers, I write down all the units. As we go along, it becomes a little bit of a burden, and I tend not to write them down until we get to the very end. So when you do the last of your math, we get that capital C is 1.3098 times 10 to the minus 8, and it's in farads because capacitance is measured in farads. So pretty straightforward. Electric energy is considered to be stored in the electric field between the plates and your capacitor. So this energy is stored, it's the work done and starts charging up your capacitor. It's stored energy. And as you discharge your capacitor, it loses energy. So they have equations for this. We don't need to memorize them. I just wanted you to be aware of them. For the larger, well, we'll leave it at that, I think. Let's talk about capacitors in a circuit, which for us is a little more important because we're going to move on to circuits in our next chapter. So you can wire capacitors together to make a bigger capacitor or a smaller one. It's a common practice with electronic devices. So if we wire them in series, the rules are that 1 over the total capacitance equals 1 over the capacitance of your first capacitor plus 1 over the capacitance of the second, and so on. The voltages or the electric potentials will all add, and the charges will all be equal. So let's look at what we mean by a series circuit. A series circuit is one where as you go along, there are no forks in the road or no decisions to be made. It just flows, the energy flows, the electric energy flows in a continuous path. So this is the battery, these two parallel lines of different lengths. If the energy starts at the battery, as it moves around the circuit, it'll go through the 6 farad capacitor and the 9 farad capacitor and back to the battery. So if we know our battery's value is 300 volts and one of our capacitors is 6 farads and the other is 9 farads, let's find out everything we can about this. So first of all, we'd like to find our total capacitance. So we know that 1 over C total is 1 over C1 plus 1 over C2 and so on. So 1 over C total for us will be 1 over 6 farads plus 1 over 9 farads. Well, 1 divided by 6 is 0.1667. 1 divided by 9 is 0.1111. When you add those two numbers together, you get 0.2778, but we're not finished because they didn't ask us for 1 over the total capacitance. They wanted to know the total capacitance. So the total capacitance will be 1 divided by this funny little decimal. So 1 divided by 0.2778 will give us C total, and that gives us 3.599 farads. V total is going to be the size of the battery, so 300 volts, and then we can calculate Q total using our formula. Q equals VC or Q equals CV. It doesn't really matter how you do it. One way or the other doesn't make a difference. So Q is going to be V times C, so 300 volts times 3.599 farads, or we end up with 1,079.91 coulombs. Remember, don't round off too often or too much. So let's look at what we can figure out for the individual capacitors in that series. We know that the 6 farad capacitor has a value of 6 farads. We know that the charges are all equal, so the total charge is will equal the charge of any one of the individual capacitors. So if our total was 1,079.91, then the charge on the 6 farad capacitor will be 1,079.91 coulombs. The voltage drop across the 6 farad capacitor will be Q equals VC, or again, it could be C times V. The order doesn't matter. So we can plug in, we know what Q is, 1079.91 coulombs. We're looking for V6, and we know that the size of the capacitor is 6 farads. So divide both sides by 6, and you end up with the voltage drop across the 6 farad capacitor will be 179.985 volts. For the 9 farad capacitor, we can go through the same thing. We know its value is 9 farads. We know its charge is the same as the charge of the 6 farad capacitor and the total charge, so 1079.91 coulombs. And we can use Q equals VC to find the voltage drop across this capacitor. And we end up with 119.99 volts. Suppose instead of in series, we wire it in parallel. The rules change. The rules are that the total capacitance would be C1 plus C2 plus and so on, that they add. The potentials are all equal, and that the charges add. So what is a parallel circuit? Well, in a parallel circuit, the capacitors are wired so that the current comes from the battery, and as it goes around, it has to split. And some of the current goes to the 6 farad capacitor and some goes to the 3 farad capacitor. So let's look how that works out. C total would be, you just add the capacitance. So 3 farads plus 6 farads gives you 9 farads. V total is the size of the battery, so 300 volts. And to find Q, we use our formula. Q equals V times C, so Q is 300 volts times 9 farads, or 2,700 coulombs. To find out the individual values, the 3 farad capacitor has a capacitance of 3 farads. Its voltage is the same as the total, so 300 volts, because it's wired in parallel. And then you can find Q from the formula. So 300 volts multiplied by 3 farads gives you 900 coulombs. We can do the same for the 6 farad capacitor. Its individual value is 6 farads. Its potential is 300 volts, same as the total. And to find the Q, we use the formula. Q equals V times C, so 300 volts times 6 farads gives you 1,800 coulombs. That finishes the chapter.